In this part of the chapter 6, we were talking about transmission line discontinuity. In section 6.2, we already discussed about the case of transmission line circuit terminated with resistive load. And so in 6.3, we will look into the problem of connection of transmission lines of different characteristic impedance. And because of the difference in characteristic impedance, we will observe reflection on the transmission line as well as transmission, which is part of the signal that goes to the following section. In section 6.4, we will look into the case of reactive termination. What is reactive termination? On contrary to resistive termination, reactive termination refers to inductive and capacitive loads, like or maybe a mixed of resistive and reactive load. And in 6.5, we will look into the problem of the so-called initial conditions, which means that you already have some current and charges distributed on the transmission line. Okay, so let's look into the problem of transmission line discontinuity. So in this case, as the figure shows, we have a transmission line coming from the left and another transmission line connecting to the right. And between them, there is a dashed line, vertical dashed line, that separates the right and left-hand side of the two transmission lines. And as you can see on the plot, the two sides are marked with different properties. The left-hand side is characterized by its characteristic impedance Z sub 0,1 and the velocity of propagation Vp1. To the right is another transmission line characterized by its characteristic impedance Z sub 0,2 and V sub P2, the velocity of propagation. And because Z sub 0,1 is different from Z sub 0,2, we will have the situation of the so-called impedance mismatch, different impedance. Then in order to, similar to the case that we have seen for termination, in order to satisfy the boundary condition, that is, the total voltage on the left-hand side should equal to the total voltage on the right-hand side. The total current on the left-hand side needs to be the same as the current on the right-hand side. In order to satisfy the boundary condition, we will observe the so-called refracted wave as well as the transmitted wave. Okay, so due to the presence of impedance mismatch or transmission line discontinuity, we will observe the phenomena of reflection and transmission. What is the significance of reflection and transmission? That is, part of the energy goes back to the negative propagating direction, and only part of the direction goes into the next sections. So in general, in the design of microwave circuits, in general, we would like to eliminate the case of impedance mismatch, because in general, we hope that all available power can be delivered to the following stage. Okay, so if you have substantial reflection that will be a waste of available energy. Okay? Now, so oftentimes in the design of microwave circuits, we will devise some technique to matching the impedance of different sections, even though that we cannot actually change the input or output impedance of different components of different devices. We can use the so-called matching circuits. You insert a section of the matching circuit between two transmission lines of different characteristic impedance, then you may be able to reduce or eliminate the amount of reflection so that most of the energy can be delivered to the next stage. All right, so as this slide says, because the impedance, impedance 这边我写电阻不太合适了哈，你可以的话把它改成阻抗值哈，交界两侧的阻抗值不同。但实际上，对于传输线的线路来讲，你的 characteristic impedance 一般来说也都是纯电阻啊，至少看起来像纯电阻啊。为什么？因为这个 characteristic impedance 指的是什么？电压跟电流的比值。好，它不是真的那个电阻哦，不是那个真的电阻会耗损能量。这边的 characteristic impedance 指的只是电压跟电流的比值。另外，除了大小的比值以外，它还代表的是电压讯号跟电流的讯号的相位。好，所以正常的传输线，它的 characteristic impedance 应该都是实数 real number， 代表的是它的电压电流比值以及它的电压电流讯号是同向的，一起变大，一起变小。啊，假如它不同向，有相位差的话，那这个 z 值就会是一个 complex number。好，当然 complex number 的话更符合所谓的阻抗嘛。好，因为这个东西我们一般叫做特性阻抗，传输线的特性阻抗。好，所以它虽然一般来讲是纯实数，但也不是不可能是 complex number。好，假如说你这根传输线，有破损啊，或者是有曲折啊，或者什么的，好，有坏有很烂，买到很烂的，或者是有坏掉的话，那它的阻抗值就可能不是纯实数了。好 ，OK， and because the mismatch, because the difference in the characteristic impedance. A reflected wave and a transmitted wave are set up so that the boundary condition can be satisfied. So let's look what kind of a boundary condition. So the boundary condition is that the total voltage and the total current on the two sides should be the same. The figure down below tries to analyze the two-section problem as the problem of transmission line terminated with loading. So you can imagine the following transmission line, the following section of the transmission line as a load. So you only need to calculate well, we would like to calculate how much, what kind of a signal is reflected back and how much energy is dumped to the next stage. All right, so as you can see here in this figure, on top of the incident wave, which are marked as V plus and I plus, you also have the V minus and I minus that are the reflected voltage and current signal. And you have the V double plus and I double plus. They stands for the voltage and current signal goes to the second section. Okay? So use these symbols, we can write up the boundary condition. So you have continuous, the voltage on the two sides on the boundary need to be the same. The currents on the two sides need to be the same. And the current signal can be replaced with voltage signal and watt and the characteristic impedance. So I plus, I'm sorry. Yeah, I plus can be replaced with V plus over Z sub 01, and I minus can be replaced with V minus divided with Z sub 01. Okay, note this I plus and I minus signals are on the left hand side, so their corresponding characteristic impedance are Z sub 01. And for the transmitted signal, I double plus equals to V double plus divided by Z sub 02. So substituting the currents with voltage and characteristic impedance, we have another equation, 6.42. So we will use 6.41a and 6.42 to solve for V minus and V double plus. Okay, so this one is known. Now this one is given. This one is unknown. This one is unknown. But you also know the value for the characteristic impedance on the two sides. So we can use these two equations to find out the expression for V minus and V double plus. But before we do that, we will introduce the idea of reflection coefficient, which is defined the same as what we done in section 6.2. We define the reflection coefficient, which is what by definition? What is the definition for reflection coefficient? The ratio of a reflected signal over incident signal. Okay. I remember last week I stressed the importance of this equation, addressed the importance of this equation to you. Okay, so again, the definition, what is the formulation for the reflection coefficient? The characteristic impedance of the next stage, of the next section, minus the characteristic impedance of the incident signal section. So it will be Z sub 02 minus Z sub 01 divided by the sum of the two characteristic impedance. So the order doesn't matter, but the order in the denominator is important. Okay, if you mess up with the order, you will end up with the negative sign, which will lead to incorrect result in your following calculations. Okay, so again, don't mess up with the order of the characteristic impedance. 那个顺序不要记错了。All right. So we also need to notice the difference between reflection coefficient defined here. Okay, so the top case is the reflection coefficient of a resistive load, while the bottom one is the reflection coefficient for two transmission connection. And the difference is RLO is an actual resistor, while Z sub 0 is just the characteristic impedance of the following section. So in this case, the following section will accept part of the incident energy and deliver to the right. while the resistive load here will absorb the incident energy. Okay, so be careful about these expressions. And because for actual transmission line to transmission line connections, we have some values, or we have some energy keep on propagating along the line. So we can also define a term that is the transmission coefficient. Transmission coefficient. And intuitively, it should be defined as the ratio of V double plus over V plus, the ratio of transmitted signal voltage over the incident signal voltage. Very similar to the definition of reflection coefficient, right? And if you take advantage of the definition of the boundary condition that V double plus is equals to the sum of V plus and V minus, you can write up the expression for the transmission equation like a transmission coefficient like this, and you notice that the two are the same. So you can be replaced as 1 plus V minus over V plus, which is the same as 1 plus gamma. So that's a very important relationship, which means that you don't have to memorize the expression for transmission equation. It's just the sum of 1 and the reflection coefficient. However, note that this is the so-called voltage transmission coefficient. Okay? In the textbook, it also defines the so-called current transmission coefficient. Forget about this, all right? I don't want to confuse you about the expression for current reflection coefficient and current transmission coefficient. We only memorize the expression for voltage reflection coefficient and voltage transmission coefficient, all right? Now, so, but it's worthwhile to take a second look about the definition of current transmission equation. Transmission coefficient is actually 1 minus gamma, okay? For voltage, the transmission coefficient is 1 plus gamma. 有注意到哈？所以我们接下去看。So, have you think about the problem that if the voltage transmission coefficient is 1 plus gamma, and we know gamma is a number, the magnitude of gamma is a real number or complex number? Well, it so far for resistive load and connection of transmission lines, the reflection coefficients are all real numbers, but they are just the special case. The general case is the reflection coefficient can be a complex number, but the magnitude of the reflection coefficient are equal to or smaller than 1 for passive circuits, for basic elements. 什么是 basic element？ 被动元件。那什么是被动元件？非主动元件。那什么是主动元件？有要插电的都是主动元件了。要插主动元件是有要插电、要吃电的都是主动元件，像那个像啥？像二极体啊，像那个电晶体嘛，但 if they are passive for passive circuits, for passive components, the reflection coefficient is always smaller, equal to or smaller than 1. Okay, so gamma is likely to be a it's possible that gamma is a number greater than 1, and tau v, the voltage transmission coefficient, is greater than 1, which means the transmitted voltage signal is larger than the incident voltage signal. Is that weird? Is that acceptable? So we need to look at it from the perspective of energy. We need to look at it from the perspective of energy. So therefore, if we try to calculate the transmitted power, which can be represented with P double plus, that is the power density, power, okay, power 因为今天讲是电场乘上磁场的话，那就是 Poynting vector， 它是 power density。但是我们现在是 V 乘上 I， 所以它就不是 density 了，它就是 power。V 乘上 I 的结果就是功率，就是 power。So P double plus, which is the product of voltages, transmitted voltage signal and current signal, can be shown like that. So even though the voltage V double plus is larger than V plus, because at the same time the current transmission coefficient is defined as 1 minus gamma. So it will be smaller than 1. So if you look at the product of this expression, you have V plus, I plus, that would be what? The incident power, total incident power. So you can replace this with P plus, okay? P plus. And in the small parentheses, you have 1 minus gamma to the square, okay? So if gamma is, which is similar, taking the magnitude you subtract the magnitude of the reflected signal. Okay, so this is the incident power. This is the reflected power. Okay, so the difference between incident power and reflected power is the transmitted power. Supposing that at the boundary of the two sections you have no resistors, no power dissipating components. If the connection contains no are lossless, if the connection is lossless, then the result is reasonable. You have the difference between incident and reflected power is the transmitted power, which is always smaller than 1, than P plus, because 1 minus gamma to the square is a number, again, a number less or equal to 1. In what cases, in what situation, you will deliver all the power of the incident power? Only when gamma equals to 0, which means no reflection, which means you have achieved the condition of impedance matching. Okay, so unless the impedance are matched in the two sections connection, otherwise some energy will be reflected back, and the transmitted energy is always smaller than the incident power. The transmitted power is always smaller than the incident power. Okay. All right. So next we can apply the bouncing diagram technique to the case of multiple transmission line connections. So let's check the transmission line condition here. Okay, let's see. Yeah, okay. So that's the largest circuit that we can have here. Okay. All right. So we have 3 sections of transmission line. They are characterized by what? Characteristic impedance and velocity of propagation. So here, I'm sorry. they are characterized by characteristic impedance and the length of the transmission line. So how do you characterize the length of the transmission line? You can address the actual physical length of the transmission line, or you can address it as the propagation delay on the line, okay? So here we use the second method. So line 1 is characterized by 50 ohm characteristic impedance and 2 microseconds propagation delay. Section 2 is characterized as 100 ohm characteristic impedance and 2 microsecond propagation delay. And the third line has 50 ohm characteristic impedance and 2 microsecond propagation delay as well. So we know that the 3 sections are of the same length, which are all equals to 2 microsecond propagation delay if they are made of air transmission line. Then the length of the transmission line will be what? 600 meter, 600公尺。在空气里头1 microsecond 的那个光速传播距离是300公尺嘛，所以其实它还蛮大的，那传输线电路还蛮大条的All right, and so we know the characteristic impedance are 50, 100, and 50. It also has a termination of 50 ohm, and the generator's resistance is 50 ohm as well. And this saves us a lot of trouble, because when the signal reaches the right hand or the left end, will there be any reflected signal here? No, because you have a match impedance case. 15 ohms terminated with 50 ohm, so no reflection. So what about the energy that goes to the right? They are absorbed by this 50 ohm resistor and are turned into what? Turn into heat. Okay? Now, and so on the left hand side, we have the similar case. 50 ohm transmission line is terminated with 50 ohm actual resistance. So there will be no reflection on the left hand side. However, because of this 3-line connection, the bouncing diagram still looks kind of messy, like the one to the right. Okay? But with some patience, we can draw, or we can accomplish the bouncing diagram, which is not a very difficult case. Okay? And so before we finish, we finish the bouncing diagram, let's look a little bit more about what signal experience within this 3 transmission line configuration. And so let's look at the right-hand side of the bouncing diagram. We know that the vertical line on the bouncing diagram represents what? The vertical line represents the time progress of the bouncing diagram. Okay? So this mark, what is the significance of this mark? This marks, I forgot to say that the circuit, the source of the circuit is an impulse signal. 稍微注意一下pulse 跟 impulse 的差别。pulse signal 跟 impulse signal 的差别我个人经验啦 ，pulse 它有宽度啦 ，like this。那 impulse 的话，比较像是你们学过的 delta function 嘛， 所以时间很短很短。但再怎么短，其实都还是有时间的宽度的啦，不过就这样了吧 ，impulse 就是很短了，只存在一瞬间，好不好？就是简单讲就是 delta function 了 ，OK 所以假如题目讲的是 impulse 的话，你大概就可以把它想成是一个 delta function。所以在那个电路上面的话，它也是画成 delta function 嘛，so the transmission line circuit is driven by an impulse signal source, which provides signals of outside a unit impulse voltage source. So it provides a 1 volt signal at t equal to 0 at this very time instant only. So it's just pop, okay? At t equal to 0, it provides a 1 volt signal. So this 1 volt impulse signal will propagate along the transmission line. And here you will experience some difference, in characteristic impedance difference. So some of the energy goes forward and some are reflected back. And here it will experience a second discontinuity. So again, some of the energy goes forward and some reflected back. And as you can see here, some of the energy reaches to the far end, reaches to the right-hand side. And the total time delay, accumulated time delay, can be found by summing up the time delay of these 3 sections, which are 2 microseconds on each. So we will, if you stand on the right-hand side, you will observe the impulse signal at 6 microseconds. What is the magnitude of this impulse signal that you observe at the right-hand side? They can be found by the initial signal, the transmission coefficient over here, the transmission coefficient over here. So as you can see here, according to 我卡住了，分压公式要怎么用英文讲？分压公式 ，voltage division， 好，听起来好像有点道理，OK， 不是什么 separate 那个不要自己发明英文了。讲个故事好了我那一年，我考大学那一年我一直觉得我的那个数学很烂我一直高中的时候一直觉得我数学很烂，谦虚了后来发现也是啦，OK， 我大学联考那个我考70几分，后来看一下，我们全班平均才50几分我们那个已经是建中第2强的班了，只差资优班而已。结果后来我看我那张成绩单我反正几年前找到的 ，OK， 我发现我坐我后面那个同学他是考100分的。我们那年就3个到台大，我们我们班有一个神他是那个台大医院的皮肤科的教授，OK， 你就知道他是台大医学系里头的第1名了然后，可是我那个，我坐我后面那个同学他是数学考100分，OK， 我觉得原因就是坐在他前面，所以让我对自己的数学非常没有自信那现在在那个台大电信所当教授玩的也都是玩数学搞死人。好，我忘记我要讲啥了，OK 那个 voltage division equation, okay. So because you have a what? A delta source, delta signal source. It has inner resistance of 15 ohm. So at the very beginning of the transmission line, it's equivalent to looking into this 15 ohm is what? The characteristic impedance of the transmission line system. So the voltage here would be 0.5 volts. Okay, so suppose that this is unit voltage impulse source. Then the V plus signal will be half volt. Okay, so you can mark that on the bouncing diagram. And at the boundary, so before you start begin with the bouncing diagram, be sure to mark the reflection coefficient and transmission coefficient on the boundary. And for this case, you need to mark the transmission reflection coefficient and transmission coefficient looking to the right and looking to the left, because you will find that the one looking to the right equals to 100 minus 50 over 150, so it's 1/3 looking to the right. But if you look into the left, that would be 50 minus 100 over 150, that would be minus of 1/3. Okay, so if you mess up with this order, you will end up with a negative sign. Okay, so on this boundary, the reflection coefficient would be 1/3, and tau equals to 4/3. On the other hand, if you look from right to left, the reflection coefficient is minus 1/3, and the transmission coefficient is 2/3. And you can do the same thing here. And you find the reflection coefficient and transmission coefficient are minus 1/3 and 2/3. Well, you can complete this expression by adding up the reflection coefficient and transmission coefficient looking from right to left. But on the textbook, this is left on down. Why? Because in the third section, there will be no reflected signal. 就像变了心的女朋友一样不回来了，所以也就没有必要写在上面了OK， 好，所以把上面把那个反射系数、透射系数都把它写完整之后，你下面再计算会比较方便一点。所以重点是你上面那个反射系数、透射系数要算对啊。算错的话，写错的话，就后面全盘皆输了，对不对？所以一开始的信号是1/2嘛，然后乘上透射系数的乘多少？4/3。所以1/2乘4/3变成4/6，也就这边 mark 的2/3。来，下一步嘞，2/3乘多少？2/3，所以就变成多少？4/9嘛。所以第一个抵达右边的讯号，它出现的时间是6个 microsecond， 而它的讯号大小是4/9。And you can continue the process of the bouncing diagram to find following signal. What is the first signal reflected back to the generator side? That would be this signal. It appears at which time instant? 4 microseconds. What is the magnitude of the first reflected signal? That would be 1/2 times what? 1/3. So that would be 1/6, 1/6伏。所以第一个弹回来讯号，在这边所看到的讯号，课本上面的图没有画，但是你可以自己把它画起来，1/6嘛。And because discontinuity are only observed between section 1 and section 2 and section 1, 2 and section 3, so and there will be no reflection at the right end and the left hand. So signal only bouncing back and forth in the middle section. So you can continue this to find out the signal size, signal magnitude in between, and find the magnitude of the signal that's reached to the left hand and right hand. So here, what is the time instance that you observe the second impulse on the right hand side? That will be 10 microseconds. Why? Because the signal shall propagate in the middle section twice to complete this pass. So that you will add up another 4 microseconds. So the time instance that you observe the second impulse will be 10 microseconds. And the signal will be 2/3 times minus 1/3, that will be minus 2/9, 2/27. So that will be 4/81 volt. The next one will appear at 14 microseconds. And the magnitude will be 4/729. How about the next one? Will appear at which time? 18 microseconds. And how about the magnitude? 4/9 to the fourth. Okay, 729再乘9嘛，那你会看到它们是一个等差级数啊，对不对？为什么？因为它们每一个后续来的那个讯号都要在这一个的左右两边各弹一次啊。一边弹一次的话是负1/3，弹另外一边也是负1/3，所以后面的讯号就会变成它的讯号就会比前面的那一个小1/9。所以很快的，这个讯号就会小到工程上面没有意义。好，你比嘛赶快。好 ，So what happens? If you have an impulse signal that is, if you have a unit impulse signal that is that this suggests the energy that you inject to the transmission line system is very limited. And those energy will be absorbed by load resistor and generator resistors on the two sides. So very quickly, the energy that you injected into the transmission line system goes away, and there will be nothing left within the transmission line system. So this is the so-called transient behavior. Okay, we know that there are signals bouncing back and forth in this transmission line system, but they only last for several tenths of microsecond. Okay, so if the observation time is large enough, then you can hardly tell anything left on the transmission line system. Okay. So let's go back to the textbook to finish the description of example 6.3. So you can see that this is the how do you find the required time delay to have signal reach the right-hand side. You just add up the propagation time required in each section. And here is the expression. You should, here's the expression for finding the magnitude of the propagating signal. So this is the voltage division equation. This is the transmission coefficient. This is the transmission coefficient on the interface of section 2 and 3. This is the transmission coefficient on the interface of section 1 and 2. And if you keep an eye on the signals on the bouncing diagram, you will find out that follow-up impulse will reach the right hand side with a 4 microsecond time delay, and the signal magnitude will be reduced by 1/9 times, okay, which are due to the reflection coefficient on the boundary of section 2. And okay, so here is the total signal that you can write up on the right hand side. That will be the total output voltage you observe on the right hand side. And so as you can see, because the source signal is a delta function, it's a delta function, then the output signal will be a series of delta function with diminished amplitude. So you can see it rise up as a summation of impulse reached at 6 microsecond, 10 microsecond, 14 microsecond, 18 microsecond. Okay? So that will be a complete expression as a summation of impulse signal on the right hand side. Then equation 6.40a is more the sophisticated expression for equation 6.47. They are essentially the same, except that the time delay are replaced with capital T1, T2, and T3. They are the time delay in those sections. So it's this is a more general expression, but it's essentially the same as 6.47. And okay, the next thing is important, which means I do not have time to elaborate that today. I will probably need to reiterate this aspect tomorrow. Because the unit impulse response of the system is a series of impulse delay in time, the response of any other excitation can be found by the superposition of time function obtained by delaying the excitation function and multiplied by appropriate constant. 直接用中文讲，因为这个东西重要哈。也就是说，你假如知道这一个传输线线路它的讯号进去跟出来的那一个特性的话，那你只要知道一些基础的 response， 比如说 impulse response， 或者嘞 sinusoidal signal response， 只要你知道这些基础的讯号的反应，在这个系统它不一定是传输线就是说在这个系统的反应，只要你能够知道的话，那么复杂讯号、复杂输入讯号的反应，就可以用加总简单讯号的反应的加权跟加总来形成，可以吗？有点像我们之前讲过的 superposition law。所以这边的话呢，我们考虑的是一个正弦波的输入，正弦波的输入，这一页很重要但你大概一次看不懂这一页的重要性在于哪里？这一页的上半部是把那个脉冲讯号改成正弦波讯号，所以你看到 delta function 变成是 cosine omega t， 有没有？所以意思就是说，我们的那个左边的那个 generator 变成是一个一直在打 sinusoidal signal 的一个 signal source。但你看6.49 上面它是 V out output voltage is written in terms of time as a time function， 但是6.49的右半部一样的 t 一样的 omega， 它只要把它改成是 phasor form 的话，它就可以 6.49 就等于左下方的这个式子。左下方的话是 phasor form， 所以它其实就是 cosine omega t 加 J 乘上 sin omega t， 但把它改成 phasor form 之后，原本的讯号，它原本的那个讯号是在 time domain 上讨论的，右上角是在 time domain 上讨论的，但你左下角就变成什么？在 frequency domain 上讨论。所以我们等于用这边偷偷在这边给你代换观念了，把一个 电路系统的 response 从 time domain 的 response 转换成 frequency domain 的 response， 因为在实务上，我们对一个传输线线路的特性的描述或特性的掌握，我们其实还是比较方便用 frequency response 去描述它的，好不好？比较常用 frequency response。所以 frequency response 你想要变成是以 omega 的 function， 然后变成看出它的 frequency response， 它可以整理成右边那个结果，那个我们明天再讲吧。但这边请你先知道，这一个大概是我们 6.3 的重点。最重点就是说它是一个 time domain 到 frequency domain 的转换。